So thinking more towards solutions, I've already mentioned in the biospheric limits, and I'm not going into the details of climate change, but energy efficiency is part of the solution to climate change by expert argument. So what we have here is a TED talk by Bill Gates showing CO2 is a measure of population, services per person, and the E is for efficiency, right? So efficiency is directly a term in that equation. And this is just analogous to the Kaya identity, which energy economists use this Kaya identity all the time. And CO2, equivalent as a surrogate for total greenhouse gas emissions, is directly modeled as a function of energy. And so energy efficiency is, to the extent these models are correct, energy efficiency is a major term in that equation, right? So here's further to that link between how energy efficiency is part of the solution for greenhouse gas abatement. This is kind of a famous McKinsey cost curve. And what this shows is, just imagine this is for global scale, but they have them for U.S. scale. This is the whole U.S. I've seen it for California. I haven't actually seen a Canadian curve, but I'm sure it exists. I just haven't really looked. So if one wanted to reduce the global CO2 equivalent, right, what you would want to do is invest the most cost-effective things first. And that's what this exercise is intended to show. Kind of going from left to right, how many gigatons do you want to reduce on a global scale? And that, of course, kind of overlays with ppm of CO2, right? So the more we reduce, the lower that end state of average global CO2 concentration. And so what this graph shows, so this is an analysis of greenhouse gas abatement. This is not intended to be an energy analysis directly. But what it shows is that all of, and it ranks things according to cost, which is an important point, and a lot of assumptions in these costs, but the ones on the left are by the assumptions of the analysis shown to have a positive payback. Crosses at 0, and then some of them have a net cost. And what this thing shows, what this analysis shows, and it's common, is that in approximate terms, the measures that have a positive cost, meaning money out of our pockets, are generally on the supply side. Measures that have a payback by these assumptions are generally on the demand side. Building insulation, right? I've been learning, building insulation, number one on the list. It's been number one on the list for at least 3 decades, I can say, from experience, right? Water heating, air conditioning, lighting, this is just all energy management 101. Now, for an alternative to McKinsey, and again to highlight people I think are really bright and have some insights, Mark Jacquard co-authored a recent study on the similar cost curve approach, and he comes up with different, he looks at what he calls a hybrid model, and he comes up with different proportions in terms of how much energy efficiency in terms of percent abatement, right? The McKinsey shows 48%, he shows a lesser amount. Carbon capture, storage, and so on. So I just show this to illustrate a different perspective, but even still, obviously, energy efficiency is a big piece of that bar graph, according to Jacquard and the SFU Simmons model. And the last slide is that one of the common ways that we achieve energy efficiency as a society, our industrialized societies, is through utility demand-side management programs. So I mentioned, of course, the obvious PowerSmart. FortisBC has their own conservation program for natural gas and for the electricity system that they have. And this is one study, there's many and I'll show more, but this is one study by a brilliant researcher we also lost this year, Lester Lave, who co-authored with one of his students about 15 years ago, where they looked at, this term negawatt, what's the cost effectiveness of electric utility demand-side management programs. So they studied using econometric, which is a statistics by economists, in my thinking. They did an econometric analysis of Northeast U.S., also where I grew up, part of my childhood anyway, in California, and they looked at that. and they found approximately 99% agreement between what the utilities reported and what they found in their independent analysis. And so, you know, in their statement, it's a pretty powerful statement to say, not only is it, you know, important, but it can be cost effective. So in review, I won't go through in detail, but there's a lot of reasons why energy efficiency is important, right? It stresses our biosphere. Some of the things we do are energy-consuming activities are not for our own good. Congestion, pollution, and so on. Non-fossil energies, the viability of really large scale, say greater than 50% or even 100% as an exercise with the Lucci and Jacobson study, it depends on reducing our consumption in the first place. Carbon capture storage, part of the solution, yes. Big uptake is, you know, huge investment and probably would take more time than we have according to Neil. Energy efficiency is a critical link to greenhouse gas abatement. We can have a better quality of life, arguably, with much less energy, and I say we as Canadians and Americans in particular, on average. And the good news is, at least part of the good news, there's large technical potential. It's been shown really for decades. 1 order of magnitude, roughly, we can do better. And utility DSM programs by some independent and very competent researchers can be cost effective. So that's the summary story as best I can on why energy efficiency is important. So like anything else, there's also criticisms of you know, why there are some, you know, why energy efficiency is not such a good thing. You know, how can anyone disagree with energy efficiency, right? Well, this one, there's one good report, International Energy Agency, kind of systematically goes through responding to the critics about, you know, rebound effects, economy-wide rebound effects, and so on. We'll talk a little more about those. You know, part of the criticism I do want to mention, one of the things with energy efficiency I'll get to a little more is the kind of invisibility of it. You know, it's hard to visualize or see or believe that it's real, something you didn't use in the first place. And part of these criticisms really are due to that, in part. This is a study just released like 2 months ago. The DSM in Canada, as best I can tell, the first study of electric utility demand-side management in Canada by Professor Jacquard and Professor Rivers, who was a student of Marx and is now a professor at the University of Ottawa. And they did an econometric analysis from 1990 to 2005 of all DSM expenditures in Canada, $2.3 billion over 16 years. And the net result, nothing, no energy savings discernible by their model. There's those who argue, so Smill in multiple readings, this one in the high impact journal Nature, where he says long-range energy forecasts are no more than fairy tales. You know, he quoted here, you know, why argue about this about, you know, CO2 and energy and so on, the various issues we're talking about, you know. I mean, you can read the quote. He's basically saying, why argue about plausible rates being more efficient if in the long run it increases our consumption, right? He describes lots of evidence that it just leads to more consumption. And one of the terms of that you'll find in the literature is something called backfire. And here's another study. It concludes that improving energy efficiency lowers the price of energy, leading to greater use. This one by Herring, 2006, is often cited. And in fact, he didn't actually analyze this, but, you know, more effective thing is to concentrate on non-fossil fuels like renewables. So this is part of this paradox, this tension, conundrum, I called it, where, you know, what are we supposed to do? The renewables people say we need efficiency. The efficiency critics say, forget it, you just need more renewables. So you really can't win in simplistic form looking at these two camps. So their challenge is, you know, to find solutions. And I'm not ready to claim any Nobel Prizes here as far as the solution. It's going to be suggesting some approaches to find better solutions. So again, some of the key challenges, I already mentioned, renewables need more efficiency to be the dominant uptake or the major source on our supply side, but efficiency leads to increased consumption. So of course that defeats the whole purpose, right? Cleaner fossil fuels have a role, but time and cost constraints to get major uptake, specifically carbon capture and storage. And then we have conflicting evidence. We have literally one of the brightest policy researchers in the U.S. and arguably internationally showed DSM's effective in the U.S. And then we have someone who's every bit as respected here in Canada says nothing, no savings, right? So there's conflicting evidence on, this is referring to utility DSM costs. So these are just a few of the key challenges of the supply and demand side. So this is where, I'm getting into more my views and more my opinions on things. I'm very open to being criticized. As a matter of fact, I hope I get some challenges here. I studied engineering. I practiced a lot of engineering and did my PhD in a quantitative policy analysis. And in my opinion, the starting point is really make use of tools that work, which are sound scientific methods. They really work for physical systems and they work for social systems too. And one of the things, just begin with better definitions. I think in my own experience at least, and in the reading, part of the problem in this world of energy efficiency is we don't really have clear terminology. So people are perhaps disagreeing over something, well, they aren't actually talking about the same thing. They could both be right or both be wrong. So what is energy efficiency? This is an article I like to cite. Of course, at least one of our students in here will probably recognize this. But so as engineers, we're used to this thermodynamic definition, first law, second law, right? That's chapter 1 of thermodynamics, chapter 1 of almost any book on energy you pick up that deals with the physical aspect. But there's also physical thermodynamic efficiency. I worked for a few years. I still do some consulting in my old group, Power Smart Engineering. We often deal with physical thermodynamic measures, like maybe tons of bulk per kilowatt hour, or in cars it would be miles per gallon. So there's other definitions of energy efficiency. And there's economic thermodynamics. So economists really have looked at energy per unit GDP. One of the oft-cited great achievements in energy is China had achieved a really huge reduction in the energy per unit GDP over a few decades, right? And if you inverse that would often be called productivity. I should say there's no consensus on these definitions. And then there's a pure economic definition where, let's say, the operator of an industrial plant might really just care about energy costs per product sales, right? They're not talking joules or kilowatt hours or BTUs. They care about cost, efficiency of energy costs and sales. And what is energy conservation? There really is no definition by consensus. So for example, Backlot's Mill, who I respect tremendously, is quoted as saying, there's 150 years of evidence that energy efficiency causes greater energy consumption. And in other writings, they'll say 150 years of evidence that energy conservation causes increased consumption. So the same term, is there's no consensus I've looked that I can find. So I'm going to go and stick my neck out and advocate that we use the term energy conservation to mean for a specified system that the primary and final energy reduces over time, whether energy services change or not. So I want to talk a bit about how to establish energy savings. Okay, so I'm talking energy savings, but this is generally true. Choose a system boundary very carefully. That's geography, a population, an engineered system could be a plant, a car, or whatever. Choose temporal boundaries, time, start time and end time of what you're going to calculate savings. Be clear, specific about policy or program. Savings due to what? The Rivers-Jacquard analysis was due to DSM expenditures, that $2.3 billion. Establish a counterfactual. So this means what would happen if we didn't spend that $2.3 billion? What would happen if this industrial plant did not accept that Power Smart subsidy? Predict what might happen with the intervention that's of interest. And the savings is just the difference between number 4 and number 5. And I just want to highlight the greatest uncertainty is number 4, right? How did you know what would have happened without? That's kind of the invisibility. Savings or efficiency compared to what is always relative to some condition that we never can measure because you can't have two things happen at the same point in time.